Dr. Pinto. Right. So the first things first. What kind of a name is 42? It is meant to be somewhat humorous. Maybe you know from popular culture, 42 is the ultimate answer to life, the universe, and everything, according to some books, radio series, movie, whatever. The Hitchhiker's Guide to the Galaxy. If you're familiar with those.
Yeah,
so,
of course, yeah.
So they spend the first book figuring out this answer to life, the universe, and everything. But and to tell the whole story of that, it took a computer millions of years just to come up with the answer. By the time they'd found the answer, they'd forgotten what the question was. So so you know, that's why they have to write more books. So yeah, so it's meant to be taken with a little bit of humor, and you should always be a little careful about what answer a computer gives you.
So there is a it's not just humor. There is also some hidden teaching in this choice.
Well, yeah, the best jokes are true.
Yeah, very true. Thank you. All right. Well, now we know the students need to go and watch the Hitchhiker's Guide to the Galaxy then.
Yeah.
All right. Thank you.
All right. Sure. Okay. So what I'm going to do now is run through some demos. I do have a case in 42 that's just called 42 demo. You can run this yourself. And it showcases several things. Usually, when I show it to somebody, we run through it in like 5 minutes. But we have more time here. I'm gonna do it at a more leisurely pace. I'm trying to figure out how to zoom in a window here.
And I want to tell you, Eric, there is a little bit of a background noise coming from your mic. I don't know if you moved or it's rubbing against something.
Okay.
Nothing has changed.
Yeah, I don't know what it could be, but okay. Did it change?
It's still a little bit like, I mean, at least in my end, but it's okay. Go ahead. I don't want to stop. Yeah.
All right. There we go. Just making that a little bigger. So I'm going to take a little more time and point out a few things. So I start just by typing 42 demo. And what it's doing here is it's looking in this demo folder, and so it's getting all its inputs from there.
And Eric, sorry if I interrupt you, but just for the sake of our students who are not familiar, you are inside of a Linux environment right now, right?
I'm running on a Mac, but
okay.
A Mac has it's basically built on top of Linux anyway, and they give you a terminal window. So yes, it acts very much like a Linux environment.
Okay, thank you.
Yeah. Oh, and please, if you have questions, shout them out. I have an outline here, but it's very flexible. I'm just going to wander around. So the first thing that pops up when you run the demo is a Voyager spacecraft in orbit around Saturn. I did this, it's kind of a glam shot. Of course, the Voyagers didn't orbit around Saturn, but I took the liberty there. And one of the things I spent more time than I should have, I'm sure, was just doing things like learning how to draw the shadow of Saturn on its own rings, and learning how to draw the shadow of the rings on Saturn. The graphics in 42 are built on the OpenGL graphics library, but I did all the coding myself, so I had to learn some things in the process. I'll also point out here, I don't usually get the chance to, that this menu over here on the left has a lot of things on it. Something that is usually overlooked is that you can focus on a spacecraft like I typically do, okay, and I can just adjust my distance here, but I can also focus on the world that it's orbiting, or its reference orbit, or any particular body of the spacecraft. So if you want to zoom in on something, you can do that.
The graphics, the graphics is amazing, Eric. I mean, you are not giving yourself enough credit. I mean, it's Hollywood really, more than, it's spectacular. That Milky Way that is,
yeah.
I mean, yeah. So, but just all around amazing. Thank you.
Well, check this out. This is the gamma ray sky according to the Fermi Gamma Ray Space Telescope.
Wow.
I worked on Fermi, so I threw that in. Yeah, and one thing I have promised myself over the years is that I will put at least as much dynamics into 42 as I do graphics, because you can get carried away doing graphics.
Do you have asteroids in the
yes.
field? You do?
Yes, I'll show one a little bit.
So is it possible, do you think, I'm thinking about group 1 that was talking about autonomous navigation, is it possible for them to simulate what the spacecraft would see in terms of looking at an asteroid with a stellar field in the background?
You would have to add something, I think, to work on that. So, right, the answer is, yeah, it's in C, so you can add whatever you want. But okay, if you look at how I draw planets when they're far away, you could use that to also draw the asteroids when they're far away. I don't think I put the minor bodies, the asteroids and comets. I don't think that I put them in view unless you're close to them.
I see.
You end up drawing things in 2 layers. You draw everything that's far away, and then everything that's close.
I see. Yeah.
Yeah.
Okay.
But if I don't have them, they can be added, and I can show you where.
And is there light parallax? Is that too small an effect to include it, or is it in there?
Light parallax.
You mean
from the fixed stars? No.
Okay.
I
mean, these things don't go very fast. I mean, typically, if you are under 30 kilometers per second, it's not worth it, But
yeah. So yeah, it's true that I did limit the scope of 42 to only our solar system and only for the next 100 years or so, because I figured I'd be retired by then.
Okay. Yeah. Got it.
But one of my mottos is anywhere in the solar system. So I did want to be able to capture anywhere that I might be looking to to work on in the foreseeable future.
Is Pluto part of? Did you put the recent topography of Pluto from the flyby?
You know what? I have not. Okay. My Pluto map is old. I'll put that on my to-do list.
All right.
All right. So moving on from Saturn, here I've got a couple of things orbiting Jupiter. You will, right? Fans of popular culture will recognize the big black monolith from 2001.
Oh, yeah. Of course. Wow.
and I threw in my Moai. This is an Easter Island style statue. And there are actually a couple of things I'm showing or demonstrating with this. One is, I've activated body axes. Okay, so I've got a body 1, body 2, and body 3 axes. So that's just X, Y, and Z. And what I did with the big black monolith is I actually started it spinning about its intermediate axis of inertia. So we were talking about the motion about spin about the intermediate axis is unstable. Well, here it is. Folks call this the intermediate axis theorem, or there's some long name that I can't remember that goes with it too. But it's not just a random tumble. You can see that it'll spin a couple of times and then flip over, and it'll spin a couple of times and then flip back over. And it's actually a regular motion. And I didn't do anything special to start this up. I just gave it a spin about its intermediate axis and a very small angular velocity in some other axis to start the motion off. So the other thing that I can show here is that the idea of a reference orbit. So these two are co-orbiting. They're sharing a reference orbit, which I've made a coordinate system here to actually show it. These brown lines show the motion of these bodies with respect to that reference orbit over, this will go an hour in the future and an hour in the past. I don't know which is which on these things. But 42 supports this so that you can do formation flying, precision formation operations. And the other thing I wanted to show, I'm actually going to start it over to show that so that they're close together again. Maybe you saw it. The MOI and the big black monolith cast shadows on each other.
Yeah,
and
that is amazing. That is amazing. Yeah.
And that's another thing I spend entirely too much time on is drawing shadows. But
do you have a background in computer in 3D graphics?
Nope, I picked it up as I went.
Wow. I mean, it seems impossible. If you think about, the famous coffee cup, the teacup challenge, the teapot, right? Yeah. The teapot challenge. Yeah. Yeah. I mean, this is more complicated than that. I mean, it's really amazing.
Yeah. So yeah, I wanted to show that I could cast shadows, both a body cast shadows on itself, mm-hmm. And on another spacecraft, because sometimes that's important.
In terms of the numerical integrator, are there options, or is that a default choice? What's the engine?
So I use a 4th order Runge-Kutta for everything. Okay. I actually have a couple of them going. I've got one for attitude, and if you enable orbital degrees of freedom, I've got another Runge-Kutta for that. I see. Yeah, once upon a time, and they're fixed time step too. Once upon a time, I tried a variable time step, but it just wasn't. It wasn't worth the overhead. Very typically, I've got a control system running, and a control system will run at particular time steps, and so it's just it's so easy to run everything at a fixed time step that works with that, and just interacting with a variable time step integrator just made things more complicated. It wasn't worth it.
Yeah, I mean, and I am less familiar with the rigid body dynamics, but usually the variable time step makes sense when you do collisions and the gravitational n-body problem, but you probably don't have the need to adaptive integration in rigid bodies, or do you?
Yeah, well, that's true. If you're, I have done some contact dynamics, and typically you do have to use a very short time step to capture those decently well. There's always a compromise you're going to make, whether you catch the collision, and adapt your time step to catch it exactly, or whether you soften the interaction a bit so that you can catch it with a finite time step. Computers, just like all of us, don't like to be surprised. So you need your time step to be small enough that the integrator isn't caught totally by surprise. And in a case like that, you might be motivated to have a variable time step so you can capture those very short dynamics and then be able to do. But nobody does month-long simulations at a millisecond time step.
Right. That's right. That's
usually,
what I'm saying.
You're solving two different problems when you do that. So
yeah. Okay.
Okay. So moving on from this, this again is this is an EOS aura in orbit around the Earth. And I'm going to move up to the map, show the map a little bit. So, right, obviously this is the map of the Earth, and I've got orbit traces for all the things in this folder that are orbiting the Earth. This one, aura, has the brighter orbit trace. So you can see we're just going over the pole, going over Alaska. Some features here, I've got a yellow circle where the sun is. I've got a moon shape where the moon is. Over here at midnight, I've got a red anti-sun. Sometimes it's useful to know where that is. And I've got two shadows. Since Aura here is my main spacecraft, I want to know that the darkest shadow is at Aura's altitude. Where is the shadow of the Earth? So it's just passing out of eclipse now, but the ground under it is still in night. So this less bright is where the shadow is on the ground, where the Earth's shadow is on the ground. So you can divide, day from night from eclipse at spacecraft altitude.
Can you, you were talking about implementing constellations. Can you, so for formation flying, the question would be, can you have a control system that maintains formation in 42?
Yeah, so for a lot of these things, my short answer is going to be, of course, it's in C, you can write anything you want.
That's a dangerous joke, though.
Yeah, I know. So I'm gonna start over. To do formation control, all you need is you need enough of the information in one place that you can do the proper calculations, and then of course you need the sensor models and the actuator models to do it. I'm gonna fast forward again, and here's Space Station. And I've got, I'll give the ProxOps view again, because I've set this one up. So here's the Space Shuttle Atlantis doing an underfly. And again, this brown trace is its path relative to the space station over time. And I have a very simple attitude control scheme on my shuttle here, so that it's always pointing its upper axis, its open bay, towards space station. Right? There's no reason it would really do that, but just to show that you can. Let me focus on that space station actually is. And then we'll let it go forward. And you can see as it underflies, it changes its attitude to keep its bay pointed toward the space station. So all you need is information, the relative state information, and then you can implement your control law on either or both spacecraft. And there's a place in 42.
Can you explain? Sorry, sorry for interrupting. Can you explain vaguely in where one would go to implement such a control, such as the
Right.
Thank you.
I was just going to say actually. So if you go into 42, there's a source folder where all the let's say all the C source code is, and hopefully if you want to talk about actuators, you go there. If you want to talk about dynamics, you go there. If you want to talk about flight software, like your control laws would be, this is the file you go into, 42fsw.c. And in it, I've got several examples. Spinner flight software, momentum bias, 3-axis. The space station we're looking at here is actually running a custom model here. If you're just starting out, I would suggest you start with this ad hoc flight software. So it's just got a very simple control law in it, and you can use this as your jumping off point to build whatever you want.
So building whatever you want means the coding in C is required to do it. Is that right?
Yeah, you can do some very simple things with just an input, not there, just an input file. But you're I don't know. I want to say that you're going to come to a point where you're going to outgrow that. And if you want to write your own custom control law, you're going to end up doing some C programming.
Okay.
Now, looking in here for a file called the input command, and I'm here in the demo folder. So here are a few things that I've set up. For example, I was just talking about the space station or the shuttle. I would set it up so it's pointing as open bay at the space station. This is the line that does that. I'm saying at time equals 0, point spacecraft 5's 0th body, that's the main body, primary vector 0, 0, -1 at spacecraft 4. So I've got what I call a prototype flight software that allows you to set up some definitions like this. And if you want to get something up, really fast, and you're not interested in the details of the actual dynamics or control, for visualization purposes, situational awareness, you can get a good first start with this prototype flight software and this kind of command script. So there are several things in the demo, right, that use this. And yeah, when I've got something I want to get up and I want to show somebody, right? If you're in low Earth orbit, you want to point your solar array at the sun, you want to point this antenna at the moon, you want to point this at that. You can do it with this kind of an architecture, and you can get it up pretty quick.
What is it that you cannot do with that?
Anything that requires you to make decisions over time, because once you set it up, right, it just goes. But if you're going to, I have a series of inertial targets that I want to visit once in orbit, say, and I've got requirements on how fast I have to slew or how tight I have to point. The details of your control law, you're gonna get to the point where you want to customize those.
And I wanted to ask you, does 42 account for fuel used during ACS maneuvers?
Yeah,
moment of inertia, stuff like that also.
You'd have to add that. I actually have added that for Roman, but I haven't migrated it out to the the main version of the open source version of 42, because it's a pretty niche thing. But if you're interested in doing that, I can show you where to put your function.
I thank you. Thank you. Well, the excuse is that so our sales don't need that, but we'll still. I wanted to understand the interaction between fuel management and the rest of 42. So thank you for that.
All right. So okay, so that's space station and the shuttle. What's next? Yeah. Okay. This is just some notional deep space ion drive spacecraft, and I'm going to highlight my local vertical axes so I know which way is down, so I can find what I'm orbiting. This is the comet that Rosetta went to. It's called 67P CG, and I think CG stands for Churyumov-Gerasimenko. All right.
I think you're right. I think you're right. Yeah.
All right. That's why I call it CG, just because it takes a long time to say those. But anyway, so I've got a geometric model of it, and I can put the spacecraft in orbit around it, and modeling the orbit around a minor body is a little bit different than around your average planet, because you have to at least be prepared to model the non-spherical gravity is very, very strange.
What and so how is that done? I mean, do you do numerical integration or spherical harmonics? I mean, how is that done?
Yeah, so for most of my orbit dynamics, I assume a Keplerian orbit as my reference orbit, and then I can do perturbations from that using a couple of different methods. My favorite is Encke's method. When you're around a minor body like this, the idea of a Keplerian orbit really kind of breaks down. It's not a good model, so it just end up with a brute force integration of your position and velocity. It's called Cowell's method, but it's exactly what you would do if you just sat down this with a totally clean sheet of paper. You'd say, I'm at such and so a position, I've got such and so a velocity, this thing is pulling me with such and so a force, I'm going to numerically integrate X, Y, and Z, Vx, Vy, Vz, right, just based on those forces. And the tricky part for this is that you have to do that because the gravity here is so non-uniform that like I said, the Keplerian model isn't a good one.
Along the same lines, do you do lunar mass cons? Are they included?
I don't. Okay. I don't. I do have. Well, I guess I do in a sense. I've got gravity harmonics for the Earth and the Moon, and I think Mars. So you can model the Moon's gravity up to probably 18th order,
okay,
something like that. Yeah, frankly, I don't know if that's the best way to model that. I suppose it's probably okay. But I've never needed anything more precise than that. So,
and these asteroids that you're showing, are these realistic shapes derived from the science?
Oh, this shape here is derived from pictures that Rosetta took of it. Rosetta went into orbit around this thing and dropped a lander called Philae, if I recall. and I think they eventually crashed Rosetta into it.
Yeah, I mean, there was an ESA mission, right?
Rosetta was ESA.
Yeah, I said, sorry, I said it the Italian way, ESA, yeah. So,
that's interesting. Okay.
Sorry, ESA. So, and yeah, and I remember that the lander is the one that bounced a few times before coming to rest, in the shade of something, I think, right?
Right. I think in the shade of this cliff somewhere.
Yeah.
And the other thing I've highlighted on here, I've got a red region, which is, that's not a realistic color. I put that in there because I've got an actual geometrical shape somewhere that is representing this region. I was interested in modeling a touch and go, like OSIRIS-REx did with its asteroid, comet.
Yeah.
So I had reason to be interested in modeling that kind of procedure. So I put a region here for me to interact with. It's a more detailed model than the rest of the terrain. Fictitious, but detailed, so I could interact with it.
And the density is presumed uniform?
They don't have a better way to do it yet. You can model the gravity by using the shape model and assuming uniform density, and that's kind of the best we can do at this time. You could build up a point mass model and then fit it to your orbit data, just like the you could do that, but I don't know if anybody does.
All right, but the question is, I guess, does the fact that now 42 has to do a numerical integration of this shape, does that significantly delay the propagation?
I don't think so. That's an interesting question. I haven't had a complicated enough system to really notice. The things that'll drag your simulation time down are if you have high frequency flexible modes. Right. And drawing shadows. That's kind of expensive. But you raise a good point. I have not looked at what the computational loading is based on. I tend to, I got to say, the geometrical model I was given for this had something like 3 million points. What you're looking at now has more like 10,000 points. I simplify these things just because I don't want to be carrying all that data around. And so I probably get some benefit, just in terms of drawing it and updating the gravity model and things like that, just from that simplification.
Still very accurate though, so.
Yeah.
And I want to do, if I might, Eric, just 1 second, because we got about 15, 20 minutes. I wanted to tell the students who are involved in projects 1, 2, 3. This is a unique opportunity, and I'm sure that Eric will be patient with any questions. So if you got them, this is your time to talk, because you have the great master right at the microphone. So don't miss the opportunity. Thank you, Eric. Go ahead, please.
Sure. And yeah, let me echo that. Please, I'm happy to field questions. So what I've got here are 3 CubeSats running in a passive constellation, a passive formation. Again, you can see their relative orbit paths here. And I'll zoom in on each one, but they're, if I can figure out how to use my own controls here. There's a 1U cube, there's a 6U cube out there, and a 3U cube. So just to show that I could draw CubeSats, I put them in formation with each other. Right, just to watch them go.
And when you do that, do you is there any flexible joints implemented in these CubeSats, or are they assumed to be rigid?
These are just rigid.
Okay. And to connect to the first hour that you spoke, can you say something about how you implement these flexible joints in 42, realistically? I mean, how is this another piece of C coding, or can it be done from a menu or something like that?
Yeah. So let me go into a spacecraft definition file. Let's pick on Space Station. Space Station is my record holder for number of bodies, right? It's got 16 bodies, and they're all connected by joints. Excuse me. So, right, this is just a quick demo. Obviously, these mass properties are very wrong, but who cares? But I've got a bunch of bodies and a bunch of joints. Okay, so I describe each body just by its mass, moments of inertia, location of its mass center, and this geometry is used to draw it. The same geometry is actually used to compute aerodynamic drag and solar radiation pressure. So, for instance, your solar sail, the very same thing you draw is what would be used to compute solar radiation pressure. Oh, there's a question? Go ahead.
Yes, Mr. Stoneking, so is it possible to phase the sun at specific points since you are trying to utilize the solar radiation pressure at its highest rate?
Yes, you could do that through the command script by saying things like at time equals this point, say my z-axis at the sun, and then at some other time point my y-axis at the sun. So you could go, face onto the sun and then edge onto the sun, and you could do this as a function of time. You can also, I think, do some events. I'm not sure if I've got it in the baseline version here, but you can do some things like at eclipse entry, do something. At eclipse exit, do something else. So you could set that up as more event-driven than time-driven. To go more complicated than that, then I would probably start writing in C.
Yeah, thank you.
Mm-hmm.
And when you were saying, Eric, about the solar sail, the implementation of a solar sail, of course, in a realistic model of a solar sail, it's much more complex than a perfect, like the cannonball model or something like that. Can this be done in 42? Can you?
Yeah. Yeah, that's the way it's done. I don't do cannonball models. If you want a cannonball model in 42, then your geometry should look like a cannonball.
I see. Oh, okay. So it knows what to do then based on the geometry. I see.
Yes.
I see.
Yes. Also, your material properties. If your surface is totally reflective, then your solar pressure is different than if it's totally absorptive or diffusely reflective. And you can set those material properties in your geometry definition. There's a way to do that, and then 42 will do the proper accounting of that.
Wow, amazing! Thank you.
So you're asking about joints. So this is the joint definition. So this joint, it's joining body 0 and body 1. It's got 1 rotational degree of freedom, no translational degrees of freedom. I have the capability to lock joints. This is kind of a handy thing to do if you want to model something, you know, freezing up in the middle of a sim or something like that. You can set your initial states, and here's more information about where the joint is and how it's oriented and such. And important for your energy dissipation model of Explorer 1, you can put in passive spring and damping coefficients in the joint. So just by setting this passive damping coefficient, you can put in some energy dissipation and watch your minor axis spinner go in and become a major axis spinner.
Now, this is interesting. So in the International Space Station, in the default model, do you have, so if you wanted to, would the International Space Station in the model that you have do this flip from minor axis to major axis? Could you do that?
Wow. Yes, you could, but don't show it to anybody. You'll scare them.
Yeah. Well, it's I like to push things, you know. So that'd be. I mean, it would happen, though, right? I mean, if you got all these components in there, I'm sure that it can be done.
Yeah. If you're looking at the dynamics of it, I would just do the big black model if there's something simpler.
Okay.
Yeah.
I see.
Yeah. I should emphasize that the model I have here for the space station is very notional. All right, you know, nothing in that thing is as light as 100 kilograms. You'll learn no dynamics from modeling this space station. It's all about the geometry and the orbit geometry and like that. Yeah. So the next thing in the demo is control moment gyros. So you may have learned about reaction wheels as an actuator for exerting torques on the spacecraft. Control moment gyros are another approach there. And the idea is that maybe you've seen this demo in some science museums. Somebody gets a bicycle wheel and spins it up, right? And they're holding on to it and they sit in a chair. So when they tilt the wheel, the chair rotates and they tilt it back and you can rotate the chair. So if you have something that has some healthy angular momentum in it, then by torquing how it's oriented, you can exert torques back on yourself. So I modeled this in 42. These discs here represent the CMGs, control moment gyro. And so by controlling their orientation with the main body, I can slew back and forth. And I just wanted to show that I did that. These are modeled in 42. These are modeled. Each one is its own separate body.
I see. Huh. Could you so would you not, I mean, is this to simplify that you do not have the connections to between them?
Yeah, that's just visual. That's just visual.
Okay.
I'm too lazy to draw all the brackets.
Okay.
But the important part is the dynamics. And if you're looking carefully, you can see the orientation of the discs change a little bit.
Yeah. And first of all, I think, Eric, there is a question that some student was asking me now. I think that they don't know if you can answer questions on connection to Cosmos. Can they ask you a question about that?
Yeah, I think Dave McComas probably has a better feel for that.
Okay.
He has kind of made the connection. So, you know,
okay.
I like 42 to play well with others. So it's good that people are using it as as an element of their larger architecture. I don't know much about those larger architectures.
And so that in that case, I'd be selfish and ask, you told me in the beginning this morning to follow up on the Jupiter issue.
Yeah.
Can we talk about that?
Right. So let me jump to this demo here. I'm going to do 42TX. This runs a case which TX is for transmit, and I'm going to do 42RX. RX is for receive. And what happens here is now I'm running 2 copies of 42. The first one is doing all the computations, and then it sends information over a socket, which is the way the internet works, to another version of 42. Only the receiving version has graphics going. The transmitting version does not have graphics going. So this is, I can do all my computations in one place, send information so that somebody else can draw it.
Wow.
And what do I decide to send across the socket is partially defined by some things I put in the code, and then I have some Python scripts that automatically take that stuff and turn it into C code. So here is some C code that was written by another program. That program was written in Python. I have learned enough Python to do this, and of course, Python is one of the back ends to Jupiter. I'm actually nowadays learning Julia, excuse me, Julia, which is another language. It's the other back end of Jupiter.
I didn't know that Julia. So when you say the other back end, what do you mean that they are both portable to Jupiter?
Yeah, absolutely. So I can when you open a Jupyter notebook, you can choose what they call it, the kernel.
Right.
And that's the computational engine. You can choose to have a Julia kernel. Let me see if I can fire this up.
When we install it from Anaconda, that is what you're doing right now, typically we end up having Python 3 in there.
Yeah. Maybe you have to set it up in the beginning, but you can make it so that Julia is one of your choices. And as a language, I like Julia a little better. Shoot, let's be honest. I like it a lot better than Python. For one thing, it's fast, and for another thing, the whole indentation is mandatory. Bothers me. And there are other reasons why Julia looks more like MATLAB in a few other ways. So so here I go new, I can choose Julia.
Yeah.
Okay. And I'm actually playing around with other notebook systems that aren't Jupyter. Somebody made one called Pluto, which looks very clean, but it's got some things that I don't like about it. So somebody else made something called Neptune, which is like Pluto, but it takes away the thing that I didn't like. So this is open source for you. Everybody does something and somebody else says, that's great, except, and so they go do their own version of it. Right? And so it can make it difficult to find exactly what you want. But if you don't find exactly what you want, you find something that's close enough that you can tweak it and make it what you want.
Right. And so are you saying, because I was following that Python created C code for you, and that was leading towards Jupyter. I mean, how does that go to Jupyter from?
That's just I learned Jupyter in the process of learning Python, and I'm actually liking the notebook concept quite a bit. It's I have known people who've done Mathematica for years and years, but I never got into it because you'd have to pay for it. But now that there are free notebooks, I think it's a very convenient way to to grow an analysis and document it, and then just make a technical memo out of it. It's very nice.
I when I wake up in the morning, that's how I start my day. I mean, it's just and also, as I said, because LaTeX, it's like subset, it's like Ka tech that you can embed in the cells, and maybe it's the 25 years of Mathematica that also make me do that. Yeah. But the thing is that when you look at 42, it draws you. I mean, you want to know, okay, is it possible to make 42 interact with the Jupyter notebook? That's the question that
so I don't know how to make a Jupyter notebook that interactive. I'll tell you my workflow. I tend to run 42, and it produces a lot of text files, and then I will load those text files into whatever you want: MATLAB, Octave, now Jupyter, and make plots. Okay, yeah, so that's kind of after the fact.
So in connection to this, then Eric, that's why I am not upset that I cannot have the beautiful graphics because I have Windows 8, right? Which is what happened to us when. But I can still do what you do, right? By using the data, the text files, basically.
Oh yeah, absolutely.
Right. So I can import the text files into. I can import the text file. Oh, yeah, we go. Now everybody in Izmir loves you now.
This is how we live these days.
Yeah, I got many of those. Yeah, in the house. Mm-hmm. Yeah. So what is the name of the cat?
Scout.
Scout. Okay, great. So my question is, obviously you can use the Jupyter notebook to analyze the data the way that you have indicated, because first of all, you can have Octave as a kernel if you wish, but also the question is, could you start from the Jupyter notebook, ask 42 to do the calculations, return those files into 42 into Jupyter for analysis, regardless of the graphics?
Yes.
Okay.
Yes. If you look in the 42 folder, there's a folder called Monte Carlo.
Okay.
And it kind of describes the process, not using Jupyter as your executive, but using MATLAB or Octave as your executive. Uh-huh. The idea is that you generate whatever initial conditions you want, say random attitude, and then you inject those into the proper input files that 42 uses. Then you from within your MATLAB script, you tell 42 to run, and it'll go run. And when it's done, you can load in its results and then save those up. So you could do like 1,000 runs that way, compile all the results, and do all your post analysis with whatever as your executive. So if I can do it with MATLAB or Octave, I can do it with Julia, I can do it with Python.
Sure.
And you can do any of those from a notebook.
And as I said, Mathematica is now free, so that is also available as a kernel.
Yeah, I didn't know that.
Yeah. They are not very good at advertising the good news. That's the problem. But I mean, we have used it now for an entire semester. So, all right. Well, I could personally go on for another 6 hours, but I think that Scout misses you there. And but we are within the 5-minute mark of David starting, and I would just like to say that it's been such a privilege to have you, Eric, explaining all this to us. And as I will repeat many times tonight, this is a conversation that I would like to have in person in Izmir in the future, if you would like to join us and continue to instruct us on these issues. Because
I would be delighted to come visit when we can.
Yeah. And at some point, these wars need to end. So it's hopefully and we are far away enough, so no worries. Izmir is always peaceful, it seems, so it's a wonderful place really to visit. Anyway, thank you also, and I would like to thank you also on behalf of the students for these groups. Particularly, I think the group 2 has been interacting with you in the time you spent with me on on Windows 8, and I really will stay in close touch, hoping to see you in town and visit us in the future.
All right, it's been a pleasure. Thank you.
Thank you so much. Really appreciate it. So a big round of digital applause for Mr. Stoneking and his